Example 3.5. In this example, we have water that is flowing in a curved water slide. As an approximation for the flow, consider the fluid to be inviscid, steady, as is given below. From the section A to B, the streamlines are straight and horizontal, while from C to D, they follow a circular path. We need to determine what is the pressure variation between point 1 and point 2 and compare it to pressures between point 3 and point 4. We start the analysis by comparing point 1 and point 2. We notice that the streamlines between those 2 points are horizontal, therefore there is no changes across the streamline. The radius of curvature is infinite. Therefore, we could simply say that the pressure difference between the 2 points could be calculated using statics. We could simply say that P1 is equal to P2 plus gamma and the distance between them, which is equal to H12. Since we know that the point 2 is exposed to the atmosphere, we could say that the gauge value is equal to 0. Therefore, P1 is equal to gamma H12. Let's do the same analysis between point 3 and point 4. Unfortunately, in these cases, the streamline are not horizontal and we have a curved section. Therefore, we need to be able to use the equation that relates pressure, velocity, and elevation for points that are across the streamline. And we could simply write it as P3 plus rho, and the integral from B to R dn for point 3 plus gamma C3. And that is equal to the same quantities at point 4. So we could simply say density at point 4, and this is equal to V R dn plus gamma C4. If we're able to evaluate this, we could see once again that the pressure at point 4 is equal to 0 since it's exposed to the atmosphere. We also know that according to this equation, according to this graph, the normal direction is in the opposite direction of the z direction, so we could say that this equation is true. So we're going to rewrite this equation using the z instead of the n, and we could say that P3 and then it's going to be negative rho integral of 3 V0 R dz plus gamma C3 is equal to negative rho integral at point 4 of V squared R dz plus gamma C4. We know from the graph that the distance between Z4 and Z3 is equal to H43. So we could rewrite this whole equation as P3 is equal to gamma H43. And then we're going to combine these two integral in one. So we're going to simply say that it's going to be minus rho. And then the integration goes from point 3 to point 4. And then we write V squared R dz. Notice that if the section between point 3 and point 4 were not curved, and the values of H43 and H12 were the same, the differences between the pressure between point 1 and point 3, they will be the same pressures. However, because we have the curvature, we have to add this term. Notice that the value of the velocity will be positive, therefore this integral will be negative. Therefore, if we compare the value of P1 compared to P3, P1 is always going to be higher than point 3. And the reason is because point 3 has a curvature effect affecting the path of the particles in that particular streamline.